Time feels constant, steady and universal. We live by it, measure it and trust it. But modern physics tells us that's just an illusion.
Isaac Newton believed in absolute time, a universal clock that's ticking the same for everyone, everywhere, regardless of what was happening anywhere in the universe. The universe is like a giant stage and time is run by the master clock, ticking silently in the background. Whatever happens on the stage, anywhere and everywhere, the clock never changes its pace. Newton is suggesting that now is the same for everyone, everywhere. However, Einstein's famous train analogy throws doubt on this. A fast-moving train is struck at the same time at both ends by lightning. Flashes of light travel up and down the train. 2 burn marks are left on the ground. A stationary observer exactly midway between the 2 ends of the train sees a flash from each end at exactly the same time and concludes that the train was indeed struck at both ends at the same time. A second observer is exactly midway along the train, riding along with it. The moving observer sees the flash of light from the front of the train slightly before the flash of light from the back of the train, whereas the stationary observer sees them both at the same time. So the question is, was the train struck at both ends at the same time or not? Time, it seems, goes at different rates depending on who's observing. And this idea that moving clocks run at different rates has a name: time dilation.
But it turns out that time dilation is not just some interesting thought experiment, but has actually been measured. In 1971, 2 atomic clocks were loaded onto planes, which were then flown in opposite directions around the globes. When they landed, the readings on these clocks was compared to one that had been left in a lab. What was seen was that the moving clocks had ticked ever so slightly slower than the one in the lab. Not by very much, mere nanoseconds in fact, but by exactly the amount that Einstein's work had predicted. GPS satellites orbiting high above the Earth experienced the effects of time dilation. If this effect wasn't taken into account, then your position would drift by kilometres every day. If you're interested, I've made a video here about the effects of time dilation as you speed up, which seem to get bigger and bigger. Thus, if you were travelling on a rocket away from the Earth at about 1/10 the speed of the light, and you travelled for what seemed like 1 year to you, that time period would be 7 years for people left back on the Earth.
And it's not just velocity. General relativity tells us that gravity warps time too. The closer you get to a massive object, the slower your clock runs. Black holes? Well, part too close and a few minutes for you could mean centuries for everyone else in the universe.
So, if time bends and stretches depending on how fast we move, what else in physics might not behave as we'd expect? Time is just one building block of the world around us. If we look deeper into things such as electrons and photons and protons, we see things can get even weirder. If you thought time was strange, wait till you meet the world of quantum mechanics.